Hello everyone, and welcome to the Parallel Axis Theorem PostLab. So in this lab we were trying to figure out if there was a way to figure the rotational inertia about an axis other than one through the center of mass. And is there a quicker way to do that than to actually work through the calculus and change the limits of integration and that kind of thing? So you collected data so that you were able to graph the rotational inertia, kilogram meters squared, versus h. H here is the distance from the center of mass to the new parallel axis. Right? So you changed where you screwed the slab in, right, which changed the distance the actual axis was from the center of mass, and that was in meters. When you graphed that, you got a top opening parabola, but unlike most other labs we've done, one with a significant y-intercept. Now, it was a top-opening parabola, so hopefully to linearize, you did what we've done many times, which is to square the x variable. So you graphed the rotational inertia in kilogram meters squared versus the distance squared in meters squared. And then you got a straight line, but again, one with a significant y-intercept. Now, since it is linear but doesn't go through 0, 0, right, we can't say that it's proportional. Right? So this is maybe one of the few times we've seen a linear graph that's not a proportional relationship. It's linear, but it doesn't go through 0, 0. Right? If you double the distance, you're not going to get 4 times the rotational inertia because you have a y-intercept in the way. But since it's linear, we can still make a y equals mx plus b math model out of it. So the y variable is, of course, the rotational inertia. That's going to equal the slope of your linearized graph. Now, theoretically, I'm saying that that's about 0.070, give or take a little bit. Okay, and we'll look up what yours were in a little bit. Units, rise over run for a slope. Kilogram meters squared of rise and meters squared of run. And notice here, the meters squared cancels, which leaves us with a slope which has units of kilograms. So what could this slope be related to? We shall see. The x variable is, of course, h squared, right? Not h. That wasn't linear, right? But h squared. And then we have a y-intercept, which is actually significant. We have to keep it. Since it's a y-intercept, it will have units of the rotational inertia. And so it was about 0.00045 kilogram meters squared. And again, we'll compare this to yours, but it's in that ballpark. And there is a reason why I made it this big, but you'll see that in a little bit. Okay? So the question now becomes, well, why did I choose that number and this number for the slope and the y-intercept? And what should they be theoretically? How does that help us relate things? Well, let's look at what we got here. If we look at our lab results. Okay, they're kind of in 2 parts. There's a lot of stuff that I asked you to put in here. So let's first look over here and let's look at the slope. So here are all the slopes. This is actually several years worth of data. Right, here are all the slopes, and you can see that they are in the ballpark with one another. Right? On average, they are about 0.0726. Okay? On the other hand, and they have units of kilograms. Okay? Well, kilograms are mass. The only mass we have is the mass of the slab itself that was rotating. So here's the masses of the slab, okay, which is about 0.0695, and look at those numbers. They're pretty close to one another. Yeah, a little over 4%, and 4% is a little high for error for us, but I mean, you know, you got 4% error in a chemistry lab, you'd celebrate, right? So in here, I think most of the error comes from the fact that, once again, we're using the equipment in a way that the company didn't intend. As I mentioned in the pre-lab, you probably started to get some weird-looking graphs, some wavy graphs, when you were screwing the slab in all the way towards the edges. Okay? Because when you had the axis of rotation way out towards an edge, there was now a torque, a vertical torque, acting on the apparatus, acting on the rotational motion sensor, and I think that kind of threw things off a little bit. So I'm willing to accept a little bit more error here, but I mean, it's still 4%, right? So seems that the slope is the mass of the slab. What about the y-intercept? Well, here were your y-intercepts, and you can again see they're all in the same ballpark, right? It averages out to about 0.00048. But, and these were units, by the way, of, let's see here. Oh, kilogram meters squared. Right. These were the... Oh, I'm sorry. This was the y-intercepts, right? Yeah, and they had units of kilogram meters squared. Well, what else had units of kilogram meters squared? Well, the rotational inertia of the slab about the center of mass. Right? That first data point you made. Here is that value, or what you calculated in part 1. I'm not sure why this person was so crazy with the sig figs, but all right, that works out to be about 0.00046 kilogram meters squared. And again, if you notice, they're about 4% of one another, right? So it should be pretty convincing that your y-intercept is actually the rotational inertia of your slab about the center of mass. So if we go back here and we realize that the slope is the mass of the slab, which we called capital M, and the y-intercept is the rotational inertia about the center of mass, which we would call I sub cm for center of mass, right? And we plug that in right there, we get a math model that looks like this, right? That the rotational inertia about any axis parallel to 1 through the center of mass is mh squared plus the rotational inertia of the center of mass, around the center of mass. And since it's addition, I can flip the order. This is just a scalar equation after all, because rotational inertia is just an amount of inertia. This is the way it's normally written, and this is what is called the parallel axis theorem. Okay, and it says that the rotational inertia about any axis is equal to the rotational inertia about the center of mass plus mh squared, where m is the total mass of the body, and h is the distance from the center of mass to our new parallel axis of rotation. These are fairly easy numbers to measure on objects, right? Mass and distance from center of mass to the axis of rotation. And so if we know the rotational inertia about the center of mass, we can quickly convert to any other axis just by using this equation. Now, this equation is not on your equation sheet, so you need to just know this equation cold, or put it in your calculator, or do something fancy like that. But it is a very handy equation to know. It stops us from having to redo things with calculus and different limits of integration, and instead very quickly convert from the rotational inertia about the center of mass, the point we tend to derive, and any parallel axis rotational inertia. So this is an important equation, even though one that's not on your equation sheet. And then what we're going to do here is spend a little time, practicing all these things, putting this all together.